So today we're going to talk about seashells as a method of learning vecs and vops. I'm just going to go to my Math for VisFX page and scroll down here to seashells. Click on this. This is based on the paper that I co-authored with Dr. Przemysław Prozinkiewicz and Dr. Hans Meinhardt, and it is about producing seashells but also their pattern. The part that we're going to study is simply the part where we're talking about the shape. So if you look at the paper, this is described here. The rest of the paper is mainly about the patterns, which we were simulating. For right now, we're just going to concentrate on the shape. So to do that, what we're going to do is we're going to use a vecs node and a vop node. So you are required in your assignment to do both. Let's get started. You'll notice this says password protected. The name is seashell. The password is defouler. Okay, to start, if you're not familiar with vecs, vops, and Python, you can look at how to move a point along a normal. We're going to talk about that. There's a HIP file if you want. If you click on this, it'll pull that up. What I'm going to do is go through the PowerPoint first. So in here, we're going to talk about vecs and vops. So this is something that has existed for a while in Houdini, but it wasn't until Houdini 13 that they came up with wrangle nodes. And wrangle nodes allow us to use code much more conveniently. In the past, we had to create OTLs or HDAs and put code into those self-contained little pieces that went along with our HIP file. Now, we actually have a node that we can very easily put code into. So what is vecs? It is similar to C++, but what if you don't know C++? Well, here's a very brief overview. So first of all, variables. For those of you coming from Python, you're probably not used to having type variables. In other words, you don't have to define, when you define something in Python, you say Kermit equals 1, or Kermit equals 3.5, or Kermit equals hello. So these are not things that you have to worry about. In C++-like languages, or compiled languages, in this case we need to reserve space. So we have types. So when we want to store something in a variable that is integer value, we say it's an int. If it has a decimal place, then we say it's float. And if it's a triple of numbers, we say it's a vector. So these are different types that we can use. Vecs was originally written as a shading language, but it's been used for much more than that. Originally, as I mentioned, it was stored in an OTL or HDA file. Vec snippets are a convenient way to bring code directly into the HIP file without any inconvenience of external storage. The first thing to note about vecs is that an @ sign, when you see that @ sign, it indicates to create an attribute or fetch. There's also shorthands for types. So some of those are, for those of you who've done Java or C++, these will look familiar. This is what they can look like in a wrangle node. So an int would be I, float would be F, vector would be V or V4 if you have a tuple of, or a set of 4 numbers. A string is S. And arrays, of course, a little different syntax. Here I've declared the type and the name of the array with square brackets. Here you declare the type and the fact that it's an array, and then the name of the array. Statements. Statements end with a semicolon. And code blocks are delimitated with curly braces. So for those of you coming from a Python background, you're used to doing that with formatting. So you indent to indicate the body of a loop or the body of a function. Now you're going to use curly braces. There is documentation on the SciDefX website about HScript to vecs comparisons, and that can be very useful, so that's a reference for you. Looping. So this is your standard for loop or counting loop. So we set, for example, a variable to 0. So I'm just counting up and summing and adding this iterator. So what's an iterator? All I'm doing is saying this variable is an integer I. It starts at 0. And it's going to go until the value is less than 10. Once that exceeds it, it's going to quit. And then increment I. So I++ is just the increment operator, and it simply means I equals I plus 1. This is simply a statement, and this is showing the body of the loop. Now we could actually express this as a while loop. It's functionally equivalent. So this is just setting I equals to 0, I less than 10, and incrementing. Functionally, it is the same thing. It will perform the same operation. So for loops were really created for convenience. Functions look very similar. So to C, so int, so the type that it's going to return, and then my function, the statements inside the body of the function, and then the return of the value that matches the type that it is. Or a function could not necessarily return a type, and we'll get to that in a moment. So here you can see that this is returning a value. We're assigning that value to a variable. In here, this is a function that doesn't return anything. Technically speaking, it's called a procedure, but we tend to call all of these things function as languages become more sloppy in the definitions. In here, we're going to talk a little bit about moving a point along a normal as an example. So in a wrangle node, when we have it set to point, what we're doing is, in this case, we're adding to the point the random value, or a random value, multiplied by the normal. So we're moving a point along its normal. This is how we would do it in a point wrangle node. So in essence, a vex or a VOP node by default is an implicit loop. It is doing this for every point. VOPs, on the other hand, is pictorial. So it's like code blocks or like Blueprint if you're an Unreal user. So here we have the point, which is being randomized based on the normal, multiplying that together, and then adding those two values together and putting it into the point value. Okay, so this is exactly the same thing that was happening here. They're functionally equivalent. Python can also be used. There are nodes, and if you were in my 160 class, you have used Python inside of Houdini. Python is not set up as an implicit loop. You explicitly go through the number of points. So for point in the number of points for that particular node, I'm setting the position variable to be point.position, and then I'm taking the normal and adding that to that position. Now, if we wanted to do the same thing with the randomization, we would add the rand function, which I've done here, and add that to the normal. So that's just a brief comparison of the syntax and the structure of what they look like. So point, vex, or wrangle nodes, and VOPs are implicitly loops. They loop over all the points. Wrangle nodes and VOPs are now also contextual. So we used to have a VOP SOP, now it's a point VOP, or a volume VOP, or an attribute VOP, or a point wrangle, or a pop wrangle, and so on. Originally, vex and VOPs only manipulated attributes, but now they can be used to create geometry as well in the details mode. Beware of your context and your attribute type, and consult the geometry spreadsheet when in doubt, because you can look at the values that currently are contained. So what this looks like in a details-only point wrangle, what I've done here is set the normal so that we have that information randomized. I've gone ahead and set up the situation so if we were using an explicit loop, we're setting a vector so that we have the information for the points and the normals. We're setting a value, an integer value for success, and then we're going through each point, grabbing the point attribute information, and then adding those two together, and then setting that point attribute back to that point number. So this was a lot more convoluted than the other one, but just for completeness, I wanted to let you see that in the syntax as well. probably wouldn't use this, but it can be very, very valuable information for later on when you're trying to figure out, how do I use point attribute? How do I use set point attribute? So detail only once can come in super handy a lot of times. This is probably not the best instance of it, but I wanted to include that in the file. So from that point on, we're going to try out these methods, and once you're confident, we're going to move on to the seashell. Just a quick recap. Also, this file is available on my website, so you can take a look at it. You can see in here we've got a comparison of the information with point wrangle node. Very simple expression. Just remember that at means fetch or create. In this case, we're fetching. And then we can see that that's taking the grid. So here we have our grid. And we're adding that point to that grid. And then I am actually doing a facet node. This has more to do with post-computing the normals to get an exact match. So some of these nodes will actually recompute after, and some of them won't. That is dependent on the version, and it's changed over certain versions. But you can see here we have our point wrangle, we have our point VOP, and it's very similar results. If we want it exact, we just recompute the normals because this one is actually doing that. If I dive inside here, you can see it's a pictorial view of the same thing. So again, just like the screen snap that came from, that was on the slides that came from here, this is essentially you take your point information, add it to a randomization of that based on the point value and then the normal, and then add those together and spit them out back into the point. So pictorially, some people prefer this, some people don't. You can also use a Python node. Again, stickler for exactness. I wanted to get it to look exactly the same. So I used a point wrangle node to create the normal using the rand function. And then I created the Python code. Python code's a little different, okay, right here. And then a facet node in here again to just get the exact same results. Again, no post-computing being done, only on the VOP there. And finally, for completeness, a Python node that does use randomize inside of it. So again, you can do this. These are the two lines that are included automatically in a Python node, and this is just the code that you're going to use for that. You can see that this doesn't match exactly. That's using a different random function, but it is still functionally the same. So if you didn't have to have it exact, you'd be perfectly fine with that. I also included for completeness the detail versus point view, so you can see that again we have a grid, we've set up the normal just for ease, and then we have our point wrangle doing the heavy lifting. And again, this is a more convoluted way of doing this, but good information all the same. Okay?